Good morning, everyone. So welcome to my YouTube channel, Master. So today we are going to see fifth lecture on group automorphism. So let's start today's session now. Okay. So today we are going to prove a theorem or result. Okay. That is easy. So theorem, I'm writing directly. Let G be a group. Let AG denote the set of all automorphisms of G and PG be the group of all permutations of G. Then AG is a subgroup of PG. Okay. So let's prove it. So what is PG actually? PG is nothing but collection of all the functions f such that f G to G is 1, 1 on 2. You collect all the functions which are 1, 1 on 2 from G to G. That is called PG. Okay. So PG, so you take any f and G belongs to PG. Okay. And you define operation f compose G. With respect to compositions of functions, PG becomes a group. PG with respect to composition of functions, with respect to compositions of functions is a group. It means PG forms a group. You take operation composition of groups. Then this group PG, this set PG becomes a group. Okay. So here operation is composition of functions. You compose two functions. Okay. That is why I have written here f is equal to f compose G. Okay. So PG with respect to composition of group, composition of function is a group. Okay. Now what is AG? And we already know that AG with respect to composition of functions is also a group. By group automorphism. Lecture 4 Lecture 4. You see lecture 4. We have shown that AG is a group with respect to compositions of functions. Now, if I can show that, now also observe that if you take any f belongs to AG, this implies f G to G is homomorphism. One and onto. So there is an extra property. If you take any element from AG, there is an extra property. It is also homomorphism. But we do not require homomorphism to be member of PG. We need only that much thing. F G to G should be one and onto. That much we need only. हमें खाली F G से G वन onto होना चाहिए, तो ये F किस में चला जाएगा? PG में. हमें इस चीज की जरूरत नहीं है कि फंक्शन F होमोमॉर्फिज्म है या नहीं, लेकिन F अगर AG में बिलोंग कर रहा है, वो एक्स्ट्रा प्रॉपर्टी रख रहा है, वो होमोमॉर्फिज्म भी है, लेकिन हमें इंफॉर्मेशन चाहिए कि वो वन onto होना चाहिए. So we have that if you take any element from AG, it is one onto also, so it belongs to PG. Okay. Okay. So now, so what does it mean? What does it mean? It implies that, so you take any element from AG and that's going to be in PG. So this implies AG is subset of nothing but PG. Okay. Now, AG is subset of PG and AG, PG, both are groups with respect to same operation, compositions of functions. Compositions of functions we get that AG is subgroup of PG. AG is subgroup of PG because both the groups have same operation. With respect to same operation, they forms a group, and one is subset of other. So that set is become the subgroup. So AG is subset of PG, and AG and PG are groups. So obviously AG is subgroup of PG. So it's proved. So we have proved the theorem. Okay. So this is done. So this is done. Okay. Now we are going to prove another theorem. Let A be a fixed element of a group G. Okay. Then the mapping SA A is in base G to G defined by FAX is equal to A inverse FA for all X belongs to G is an automorphism of G. Let's prove it. So first of all, FA is homomorphism. How? We need to check it. Let X, Y belongs to G. Then F, A, X, Y is equal to A inverse X, Y. Okay. A. Okay. But we can write it as A inverse X, A inverse. Because A inverse is nothing but identity. Because A inverse is identity element. Okay. So it will not affect anything. So we can write A inverse X A inverse Y A. So what is this? F A X. So what is this? F A X and F A Y. Okay. So this is equal to. This implies F A X Y is equal to F A X F A Y. So this implies F A is a homomorphism. Okay. So second, F A is 1 1. F A is 1 1. Okay. F A is 1 1. Let X Y belongs to G such that F A X is equal to F A Y. Okay. So F A X is equal to F Y means what? What is this? A inverse X A is equal to A inverse X, Y. Okay. Okay. Y. So we can write this as A inverse X A inverse Y A. So apply cancellation property. By cancellation property, what we have? By cancellation property in group, this implies X is equal to YA by cancellation law in group G. Cancellation law always holds in group. Again, so this is by left, L-E-F-T. Left cancellation law in group G. Okay. Now, X is equal to Y, you can here. By right cancellation law in group G. So in a group G, cancellation law holds. Cancellation law are of two types, left cancellation law and right cancellation law. So this implies X is equal to Y. So this implies FA is 1, 1. Now F is on to. Sorry, FA is on to. FA is on to. Let Y belongs to G. Okay. Then X is equal to AYA inverse belongs to G. Okay. Now FAX is equal to, what is this? FA so FAX is equal to, what is this? By the definition of this is nothing but A inverse XA. Now put the value of X there. AY, A inverse A. So A inverse A, this is Y, A inverse A. This is identity and this is also identity. So this implies, what is AX? You are operating identity both the side, you will get Y. Because you operate identity with any element, you will get that element. Okay. So given any Y belongs to G, there exists X belongs to G such that FAX is equal to Y. We get that FA is on to. Since FA G to G, FA G to G, FA G to G is homomorphism one one and on to. We conclude that F is automorphism of G. Okay. So this is homomorphism 1, 1 and on to. So this is automorphism. Okay. Definition. What is the definition of inner automorphism? Inner automorphism. G, if G is a group, okay, the mapping F A G to G defined by F A X is equal to A inverse X A for all. This is symbol of for all. This is symbol of for all. X belongs to G. X belongs to G. Is an automorphism of G okay, known as inner automorphism. Inner automorphism. Okay, we have checked that active automorphism of G. Such type of automorphism are called inner automorphism. Okay. So I am writing a remark or no that not an automorphism which is not inner automorphism is called an outer automorphism. Outer automorphism. Okay. So a homomorphism, a automorphism which is not inner automorphism is called outer automorphism. Okay. So we are going to do one theorem on it, on inner automorphism. For an abelian group, the only inner automorphism is the identity mapping. Whereas for non-abelian groups, non-abelian groups, there exist non-trivial automorphism. Non-trivial automorphism. Okay. So this is automorphism. Okay. Let's prove it. Proof. So what are the trivial automorphism? Trivial automorphism is nothing but identity automorphism. Okay. So automorphism other than identity automorphism. We know that identity automorphism is R. So identity map is a automorphism. That is called identity automorphism. A automorphism other than identity automorphism, that is called non-trivial automorphism. Okay. So here now suppose G is an abelian group. Okay. Abelian group and Fk is an inner automorphism of G. Then Fax is equal to A inverse X. But G is abelian. G is abelian, so I can write it X A inverse. So I can write. So I should write it properly. So this is I can write so A inverse X. I can combine by associative property. Associative property in G. By associative property, I have this one. Associative property, we have this one. But G is abelian. G is abelian. I can write A inverse X to X A inverse. G is abelian. Therefore, A inverse X is equal to X A inverse. Okay. Now I can write it. So I can use associative property. Okay. I can use associative property again. So I can write this. A inverse. So A inverse A is nothing but A. So this is identity. You operate identity, you will get same thing. So this implies Fa X is equal to X for all X belongs to G. But we know identity map also satisfies this. It takes same element to same element. So what does it mean? Fa is equal to identity automorphism. Okay. So this implies Fk is identity automorphism. So this implies Fk is the identity automorphism of G. Okay. Next, let G be non-abelian group. Okay. Now, G is non-abelian group since G is non-abelian. There exists non-abelian. There exists AB belongs to G such that AB is not equal to BA because G is not abelian. So if G is not abelian, commutative property will not hold. So there will be some element A and B will not commutate because commutative property will not satisfy. If commutative property satisfy for all AB belongs to G, then G become abelian, but G is non-abelian. So there will be A and B belong to G such that AB is not equal to BA. So this implies that B is not equal to, you take inverse both the sides, so it will become BA. You take inverse both the sides, so I can, taking inverse both the sides, it will be identity here, it will become B, A inverse BA. Okay. Okay. So this implies FA B, that is A inverse BA, not equal to B. So this implies FA is not identity mapping of G. Identity mapping or automorphism you can say of G. Okay. Thus, for non-abelian groups, there always exist non-trivial inner automorphism. Okay. Automorphisms. Okay. So we have shown this. So, here you can write here inner automorphism you can write because non-trivial inner automorphism will exist. So inner automorphism. Inner automorphisms. Or you can say automorphism. Okay, same thing. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my channel. Thank you very much for today's lecture. Thank you.